Hello, my name is Aman, and today I'll be talking about Calculus 1 in Aerospace Engineering. I'll explain how Calculus 1 applies to my major, which is Aerospace Engineering, as part of our Mat 120 research project. Growing up, I always knew I wanted to become an aerospace engineer. I was fascinated by how airplanes fly, how rockets launch, and how spacecraft navigate space. But as I began learning more, I realized that understanding the math behind these systems is crucial, especially the kind of math we're learning in Calculus 1. From derivatives to rates of change, these concepts aren't just abstract, they're directly applied in the real world of aerospace systems and control loops. So today, I'll be focusing on how Calculus 1, particularly derivatives, show up in one of the most essential aerospace control systems, the PID loop. One of the most foundational ideas in Calculus 1 is the derivative, which describes how fast something is changing. For example, the derivative of position gives velocity, and the derivative of velocity gives acceleration. These rates of change are critical in aerospace. Whether you're trying to control the angle of an aircraft wing or the speed of a rocket engine, you need to know how fast things are changing and how to respond to those changes in real time. This is where PID controllers come in. PID controllers is a system that uses proportional, integral, and derivative thinking to control everything from autopilots to satellites. Let's take an example of an autopilot in an airplane. Modern aircraft use an IMU, also known as an inertial measurement unit, that constantly measures acceleration, angular velocity, and orientation using sensors like gyroscope, accelerometers, and magnetometers. This data helps calculate where the aircraft is pointing, which is attitude, how fast it's rotating, and whether it's drifting off its planned course. This raw data is then passed on to a control algorithm, usually a PID loop, to decide how to move control surfaces like ailerons, rudders, or tail elevators. But this raw sensor data is noisy and imperfect, so control systems need to be precise and responsive. This is where the power of calculus-based feedback is essential. Now let's focus on the PID section of this. PID controller loops. A PID controller is one of the most widely used control systems in aerospace. It takes in sensor data, compares it to a desired set point, like maintaining level flight, and calculates how to correct error using three terms. The first term is the proportional term. This term reacts directly to the current error. Let's say your drone is tilted 10 degrees off target. The proportional term will push it back proportionally. It's a straightforward response, but on its own, it may not be enough. Next comes the second term, which is the integral term. This term looks at the accumulated past error. If your aircraft has been drifting slightly off course for a long time, the integral will notice the buildup of error and correct for it. Mathematically, it's using an integral from Calculus 1 to sum up error over time. It's great for reducing steady-state error, but too much can cause overshoot. Let's move on to the third term, which is the derivative term. This can be considered the most calculus-heavy part of the controller. It calculates the rate of change of error, just like we learned in class with derivatives. If your aircraft starts to tip rapidly, this term reacts to the speed of the tilt, not just the tilt itself, and applies a counteracting force. It predicts future behavior, acting like a kind of mathematical intuition. The derivative term is crucial for stability. Without it, control systems might overshoot or oscillate. But it's also very sensitive to noise. A small sensor glitch could be misinterpreted as a rapid change, causing an overreaction. This is one of the biggest real-world limitations of using derivatives in control loops. Now, let's take a deep dive into the derivative term. Let's go deeper into this term since it directly uses what we've learned so far in Calculus 1. In aerospace, things happen fast. A drone might tilt in milliseconds, or a rocket might drift due to atmospheric pressure changes. The derivative term acts as a shock absorber. It slows things down before they go too far. For example, if a plane starts nosediving, the derivative term doesn't just say we're diving. It says we're diving faster every second and initiates a strong correction early. However, because this term reacts to how fast the air is changing, it's especially prone to sensor noise. If the IMU detects a tiny false change in acceleration, the derivative term might jump to a larger correction. That's why filtering and smoothing data is often used before applying derivatives in aerospace systems. Now, let's discuss some of the drawbacks of PID control. PID controllers are widely used, but they do have their own limitations. One of the major limitations is tuning, as tuning these systems are super difficult. Each system needs different values for the P, I, and D part of the equation. There's no universal solution. PID controllers also lack no model awareness. This means they have no idea how to relate these mathematical values to a physical situation. At last, another major drawback is limited adaptability. The PID controller loop is not ideal when the system's conditions change constantly, like during atmospheric re-entry or a satellite maneuver. That's why PID is often paired with other tools such as machine learning or model-based control for higher-end aerospace systems. Now, let's discuss more applications of PID controllers in aerospace engineering. One of the very common ones in the defense side of aerospace engineering is a rocket guidance system. During launch, a rocket must maintain stability in 3 rotational axes: pitch, yaw, and roll. The rocket constantly experiences external forces like wind shear, thrust imbalance, or even slight asymmetric figures in the manufacturing of the rocket. A PID controller is used to process data from onboard sensors, such as from an IMU, to detect even tiny changes in angular velocity or orientation. The derivative term in the PID loop measures how fast the rocket is rotating and applies corrective action early, before the error grows. Without derivatives in the loop, the response would lag and oscillations could build up, making the vehicle unstable. Moving on to another example, such as a jet engine throttle control. Modern jet engines need to adjust thrust smoothly and efficiently, especially during takeoff, landing, and quick altitude changes. When the pilot moves the throttle lever lower, the engine's control unit uses a PID loop to adjust fuel flow, angles of the blades inside the compressor chamber in the engine, and turbine speeds. Imagine rapidly increasing engine thrust during a go-around. If the system reacts too slowly, the plane might not gain enough speed and lift. If it reacts too quickly, it could overshoot and destabilize the plane, risking an engine surge or flame out. By analyzing the rate of change or error, how quickly the engine is ramping up, the derivative component applies just enough control to prevent dangerous fluctuations and keep the engine transition smooth. Finally, another example is a satellite attitude control. Satellites orbiting Earth or heading to deep space need to maintain precise orientation to aim antennas, cameras, or solar panels in the right direction. They use reaction wheels or control moment gyroscopes to rotate themselves without using fuel. These devices spin internal masses, and by conservation of angular momentum, the satellite changes its orientation. But even small errors in angle or angular velocity can throw off a mission. That's where PID controllers come in. If the system detects the satellite is starting to drift off angle at a growing rate, the derivative term kicks in first, damping the motion before the satellite drifts too far or has to use more energy to correct. This is especially important for deep space probes or telescopes like the James Webb Space Telescope, where even a fraction of a degree in orientation matters for accurate data collection. I hope you all learned a tiny bit about PID loops and the relation between calculus and aerospace engineering. All of this information was searched up on Google and from a couple of books related to aerospace engineering by James Anderson. I hope most of the information is accurate. Thank you.